Okay, so today we will solve mathematics get 2023 question number 11. It's question from calculus. So what it is saying, let f r to r be a function which is defined by 2x square y by x square plus y square for xy not equals to 0 and 0 for xy equals to 0 0. Then there are 4 options are given. You have to what is option number A, the directional derivative of f at the origin in the direction of 1 by root 2 comma 1 by root 2 is 1 by root 2. Option B is the directional derivative of f at 0 0 in the direction of 0 comma 1, so this is y-axis is 1. Option number C, the directional derivative of f at 0 0 in the direction of 1 0, so in the direction of x-axis is 0. And option number D is f is not differentiable at 0 0. Okay, so this is NPTEL reference. Now, so before solving this, we need few definition and results. Let's recall the definition of a differentiability of a function. So let's f is a function from omega to Rm, where omega is open subset of Rm and a is a point in omega. We say that f is differentiable at a if there is a linear transformation from Rn to Rm such that this will hold, whether in the numerator it's taken the norm in the Rm norm and this is the Rn norm in the denominator. So if this will hold, we say that f is differentiable at a. Okay, now the directional derivative of a, next, at the point a in the direction of a non-zero vector u is denoted by du of du suffix u f at the point a, which is defined by limit t tends to 0 f of a plus tu minus f of a by t whenever the limit exists. So this is called the directional derivative of f in the direction u at the point a. So this is the gradient of f, so this is the gradient of f at a. And next we need this theorem that it's saying that if f is which is a defined on a open subset of Rn to R is differentiable at a point a, then any directional derivative will exist and the directional derivative can be computed by the in terms of this inner product taking gradient with the direction u. So this theorem we will use to prove the last option. Okay, so let's start to solve the question. So first we have to find the directional derivative of f at the point 0 0 in the direction of 1 by root 2 comma 1 by root 2. Okay, let's start. So we have to find directional derivative d in the direction. So let me write first here u is 1 by root 2, so in this direction we have to find at the point, so this is denoted a at the point 0 0, so you have to find del u f at a means d 1 by root 2 comma 1 by root 2 f at the point 0 0. So this is by definition limit t tends to 0 f of, so this is a plus tu minus fa by t, right? So a is here 0 0 and t is the real number and u is the 1 by root 2 1 by root 2. So if we put this in the function, what is the function here? Let me write f of xy, so this is 2x square y by x square plus y square if xy is not equals to 0 0, and this is 0 if xy is 0 0, right? So what will happen if we put this, then we will get, you can see you will get limit t tends to 0, so what you will get 2, you will get t square by 2 into t by root 2 minus 0 by t. Oh sorry, not here, it will be by t square in the denominator, and this is minus 0 by t. So if you calculate, put this, all these things in the function, you will get this. So if you solve this, what will be this? Limit t tends to 0. This is basically t cube by t cube root 2. So it will cancel out. What we will get? 1 by root 2. So directional derivative of f at the point 0, 0 in the direction 1 by root 2, 1 by root 2 is 1 by root 2. So this is the option A. So option A is correct. Okay. So let's move to the option B. It is saying that we have to find the directional derivative of f at the point 0, 0 in the direction 0, 1. So this is basically y-axis, right? So this is also called the partial derivative with respect to y. You can, if you think, you will get that this is same as saying that finding partial derivative in the direction of y, right? So let's find the directional derivative in the direction 0, 1. So this is option number A. Or B, what we have to find? Directional derivative in the direction 0, 1, right? So d of 0, 1 f at the point 0, 0. So this is by definition limit t tends to 0 f of again 0, 0 plus t of 0, 1 minus f of 0, 0 by t, right? So if you put this in the function, what you will get? Let me write it. So you will get, this is basically 0 minus 0 by t. So it will be 0. So the directional derivative of f at the point 0, 0 in the direction of 0, y is 0. So this is basically partial derivative. So this is del f by del y at the point 0, 0. So this is 0. So option number B, what it is saying? So this is, they are saying this is 1. So this is false. Okay. Now let's check the option number 3. So we have to find the directional derivative of f at the point 0, 0 in the direction 1, 0. It is 0. So this is same the question of option B. So let's check. So option C, you have to find d of in the direction 1, 0 of f at the point 0, 0. So this is by definition limit t tends to 0 f of 0, 0 plus t 1, 0 minus f of 0, 0 by t. So again, if you calculate this, you can see that this we will get 0 minus 0 by t. So again this is 0. So this directional derivative we get 0. So this is same as, you can see that this is del f by del x at the point 0, 0. So this is 0, right? So C, it is saying that directional derivative of f at 0, 0 in the direction 1, 0 is 0. So this is correct. Now option number 2, you have to find that f is saying that f is not differentiable at 0, 0. So for that we will use that theorem that if a function is differentiable at a point A, then directional derivative in any direction is exist and it will can be computed by this. So we will use this theorem. So let's see. So this is D. So let's take this direction 1, 1. So we have to, so let's find directional derivative in the direction 1, 1 of f at 0, 0. So what will be this? So this is by definition the limit t tends to 0 f of 0, 0 plus t of 1 comma 1 minus f of 0 0 by t. So if you put these values in the functions, what you will get? You will get 2t cube by 2t square minus 0 by t. So if you calculate this limit, what you will get? You will get 1. So directional derivative of f in the direction 1 comma 1 at the point 0 0 you will get 1, right? So if f is differentiable, at 0 0, then by that theorem it should have directional derivative at the point 1 1 f 0 0. It should be given by inner product with gradient of f at the point 0 0 with the direction 1 comma 1, right? So this should be true. So let's compute the derivative. So this is the, here we use the theorem. So note, what is gradient of u f at 0 0? So this we know, this is del f by del x at the point 0 0 and del f by del y at the point 0 0. Note that we have computed these two in B and C. So del f by del y is 0, del f by del x at the point 0 is 0. So this is 0 comma 0. So now find the inner product. So then, so gradient of f at 0 0 with 1 comma 1. So what this will be? So this is inner product with 0 0 with 1 1. So this is basically 0, right? So what we got? That this inner product is 0, but we got this directional derivative of f at 0 0 in the direction is 1. So these two are not equal, right? As df d11 f at 0 0 is not equals to 0 0 inner product with 1 1. So which implies f is not differentiable at 0. F is not differentiable at 0 comma 0, right? So what we've got? Option number D is correct. So here A, C, D are correct, B is false. Okay, so question number 52 is done. Okay, let's stop. Bye.